Hello, everybody. Happy Friday. So outcome 11, we only have 3 outcomes left to go, at least the in-person ones, including this one. You are or should be working on retrosynthesis 2. If you have absolutely any questions on retrosynthesis 2, or if you want to talk through retrosynthesis 1, please let me know. My normal office hours, as you hopefully know, are on Thursdays, but if like you're in lab with me and lab always has some downtime and you want to kind of go through things, or after lab or something like that, or just if there's a day that works better for you, please let me know and I will help you with that. Retrosynthesis is the most challenging thing in this class for sure, because I'm asking you to assimilate a whole bunch of information. So it is hard. And if you need help, it is absolutely fine. You can work in a group. If you didn't work in a group on the first one, I really recommend that you do so for the second one. But if you have any questions, you can work with your group or you can talk to me. Those are your options. Going back to stuff from last semester might be helpful. Remember all of those worksheets. I wouldn't go through those and start from scratch, but kind of the process is largely the same, especially when you're changing functional groups around. If you just want me to check your flow charts or whatever, I'd be happy to. But please let me know if you need help. Please don't wait until the last minute or else it's not going to go well. The reason that you have 2 weeks to do those is not because I want you to procrastinate on them, but because like it literally takes a lot of time to kind of think through those, because those are hard. So you have one more that's currently up there and is due, I think, next week, Tuesday, right? And then there will be one more assigned after that, which is going to have a lot of these aromatic ring reactions, which we're working through right now. And that'll be the last one of the semester. So we have class today and Monday, and then outcome 11 quiz. And then next Friday, the following Monday, outcome 12 quiz, and the following Friday and the last Monday, and that'll be our last classes of the semester. So counting today, there's only 6 classes left. There's only 3 more quizzes. We're getting close. I know you're all exhausted. Don't give up. Stay with me. We can make it. I want all A's. Okay. All right. All right. So this is our first reaction, and it's going to work into our second reaction. But the idea here is that the first questions here should have been a lot of recap from last semester. I don't expect you guys to remember all of this, but I hope that you went back and kind of looked at your notes a little bit. But a lot of this was based off of what we knew from stability of ions last semester. So the first step of any alkene reaction, and that's the reactions that we're going to be doing for benzene, because benzene, it's not just an alkene, but it still has alkenes, is that alkenes are loosely held pi bonds, loosely held electrons. They're kind of floating in space. And what's attracted to electrons? The word that starts with E and ends with phile. Electrophiles. So all of these reactions will start with an electrophile of some type reacting with your pi bond. And so we'll get to that later on today with benzene rings. It's even harder, so you need stronger electrophiles, but it's still pi bonds are attracted to electrophiles. Electrophiles are attracted to pi bonds. So the H plus goes on first, and it has kind of a choice of 2 different places to go. It could go on the carbon on the left, which would make a carbocation on the right, or the carbon on the right, which would make a carbocation on the left. And it's not about where the H goes. This was Markovnikov addition, by the way. I know we remember that term at somewhere, but it was about what makes them more stable carbocation. So this is a secondary carbocation. This is a primary carbocation. What's the fundamental issue with a C plus? Gabe.
C plus has the
What's the plus charge mean?
The plus charge is that it has doesn't have an electron.
Correct. It does not have enough electron density. So what would be helpful? More carbon neighbors or fewer carbon neighbors? Correct. So which one's more stable?
It would be the first
one. Correct. And so you would never, ever, ever even get this. So this would be the only product we would get. All right. So then what would happen in the second step of this reaction? So you've got that carbocation. In the second step, you just add in Cl minus. The mechanism of this is pretty simple. Nucleophile, electrophile, brand new bond. So at the end of the day, what we have done is added a hydrogen on one side and a chlorine on the other. This was Markovnikov addition. I don't know if you guys can see that, of H and Cl. So this is what we did last semester, but it went through those 2 steps. And going through those 2 steps is going to be fundamentally important for all of these more complicated reactions that we're covering today, because it always starts out the same way. Excuse me. All right. So now we're going down to a diene. So what do we know about dienes compared to alkenes? So when they're conjugated, they have some extra stability. So two double bonds that are conjugated would be more stable than two double bonds that are isolated. But there's an interaction. So there's information, there's extra stuff going on when they are conjugated to each other. So I asked you to react the leftmost alkene just so that we were all on the same page, but it doesn't really matter because this is a symmetrical molecule. But what will happen here is the pi bond will be attracted to the electrophile and you will attach a hydrogen. So Kaylee, where will the hydrogen go? On the left carbon or the right carbon of this pi bond? Correct. It will go on the left, but it's not about where the hydrogen goes, just like this one. It's not really about where the hydrogen goes, it's about what carbocation you get afterwards. So if you were to put the hydrogen right here, you would have a primary carbocation. And if you put the hydrogen here, you'd have a secondary. The secondary is more stable. So that's the whole reason why the hydrogen goes on. So through the rest of this is really important. Gabe, this is important. Okay, we're gonna get two intermediates and two products. They do not occur because sometimes the hydrogen goes initially on the right and sometimes the hydrogen goes initially on the left. The hydrogen will always go on the left. Markovnikov addition always happens. So the first step, you only have one option. It's the whole thing why I made you cross this off. You don't get both. You only get one first step. Your first step will only be one possibility. And that will be to put the hydrogen on the left side, which would give you a carbocation on the right. So that is the only thing you would get, right, from that step. So where we end up with the possibility of two routes to follow for this reaction is that after we put the hydrogen on the left, again, the only place the hydrogen will go, you now have a carbocation that because there was conjugation before, you now have the possibility of resonance. So in resonance structures, and again, it's been a long time since we did resonance, but you may or may not remember in resonance structures, we can move lone pairs and pi bonds. And in this case, we don't have any lone pairs. So the reason to move bonds around is to spread out a charge. That's why we even approach these. The whole point of resonance is to delocalize a charge throughout a molecule because it's more stable to have it kind of at a half of a plus in multiple places instead of just a plus in one. So that's kind of why resonance happens. So what we can do here is that this carbon right here doesn't have enough bonds and we can just swing that pi bond over there. And that would give us a pi bond in the middle of this molecule, which would put the plus charge on the right. I know it's been a while since you guys did resonance, so what might be really helpful is to draw out your hydrogens. You don't absolutely have to, but it's part of how we can kind of see what we can't do. So if we notice, there are 3 hydrogens here on this leftmost carbon. So therefore that carbon, much like when we did aromatic, non-aromatic, this is kind of interrupted. It can't have a p orbital, so it can't be involved in resonance. So the only place you can move that double bond is right here. There is no possibility of moving that double bond to this spot because that carbon right there has 3 hydrogens. So that's part of the way that drawing out your hydrogens can help you. The other way that it might be helpful is it's pretty simple, I think, to hop a double bond over, but sometimes it's not so easy to identify where the plus charge is. But if you have all your hydrogens drawn in, you can tell that in this product right here, that's the carbon with only 3 bonds. Therefore, that's the carbon with the plus charge. So anytime a carbon has 4 bonds, it's neutral. But if a carbon has 3 bonds, it's got to have a charge. And those are old things, but I know it's been a while, so it's kind of, sometimes it's worth drawing that out just so that we can practice correctly. All right, so I asked you, so at this point, basically what's happened is our reaction is split. It's got 2 different possible intermediates. Which of these intermediates is more stable? Why? Exactly. So it's all about the carbocation. So there's a couple different trends to consider here. We know what makes a more stable alkene and also what makes a more stable carbocation. It turns out that those 2 trends would conflict in this case. But the major contributing factor to the instability is the plus charge. So whatever can make the plus charge more stable is the major factor in here. So this is your most stable or major intermediate. All right, and then from that point, we can just go ahead, I'm not going to draw these again, and get to our product. So the second step, much like question number 2 above, is that when you've got that plus charge, the second step of the reaction is just the Cl minus joins on to wherever your plus charge was. And notice that because I have plus charges in 2 different spots, I'll get the chlorine joining on in 2 different spots to give me 2 different possible products. It doesn't do it, you don't get a chlorine on both spots in the same molecule, but if your carbocation is at this kind of carbon number 2, then your chlorine will go on carbon number 2. And if the carbocation is in, let's just say carbon number 4, your chlorine will go on carbon number 4. And this is how we end up with multiple products. So the 2 different products we see are this one and this one right here. So when you start this reaction, the reaction was this then. One equivalent of HCl, you'll get 2 different products. All right, which of those would be the most stable product? The one on the right, why?
Because the chlorine wants to be a leading group, so I feel like the one on the left has a better position for it to be.
Your answer is correct that this is the major one, and you are right about it being a better leaving group, but that has nothing to do with its current stability. That would just be its.
Mono, and that one's
Yeah.
like trans style, something like
Yeah.
that. I don't remember what exactly.
Yeah, so remember last week we talked about stability of alkenes. So it's all about stability of alkenes. That's the only kind of unstable thing here. So this would be a monosubstituted alkene. This is a disubstituted alkene. So a lot of this, and the reason I asked you guys to kind of work through this on your own, is that a lot of these, this is all based on stuff. It's reconstructing pieces of information we knew to get already into one bigger reaction. So this would be the major product. Right, because it is the most stable alkene. All right, so we're going to write out this reaction on a kind of a blank page so that we can kind of follow along. But what we'll see is that I know that I put the bridge first and then the video afterwards. You didn't need to use the video to do this bridge, which is why I put this first. But the whole idea is looking at thermodynamic products and kinetic products. But we can look at these and we can kind of figure that out based on what we have here. So let's go ahead and we'll give ourselves some more space so we can do actual activation energy or reaction energy diagrams. And we will do that. So let's go back to our original molecule, which looks like this. Right. And in the first step, we add on our H+, and we're going to get 2 different possibilities. Well, we only get one possibility from this reaction, which was that the hydrogen goes on the left side of the left alkene. So the positive charge would be right there. And then in the second step, when the chlorine comes in, we would get that thing right there. I'm going to leave that one hydrogen. You don't have to draw it. We never have to draw hydrogens on carbons in line angle structures, but just that's the 2 things that we have. So this is just the same thing you have in your bridge. We have a resonance structure of the intermediate where that double bond can hop over. And so what we will have in our other structure here will be a plus charge on the left, still a hydrogen there. Right, and in this case, kind of this blue route, our Cl minus will again go onto the carbocation, and we would have the double bond in the middle there. It's going to be between carbons 2 and 3. And so these are the same 2 products you drew. These are the same 2 intermediates that you drew. And what you guys said, which was correct, is that this is the most stable intermediate. And that this one is the most stable product. Everybody following along? All right, so let's look at this in terms of reaction energy diagrams, which is kind of what that video is largely about. So in all of this case, you start off with the same starting material, that thing plus HCl. All right, but let's compare and contrast kind of what we get for the red route versus the blue route. So I'm just going to draw the red one and we'll just decide whether the blue one's going to be higher or lower. So we're going to have this intermediate, and we're going to have this product right here from our red route. So for our intermediate, would our blue intermediate be higher energy or lower energy comparatively? Higher, yeah. So this intermediate with the secondary carbocation is more stable, which means lower energy. So therefore, this intermediate with a primary carbocation would actually be a much higher energy intermediate. Everybody follow? Any questions on that? All right, and then let's look at, compared to this product, where would our blue product be? Lower, because the product would be more stable. Oops. And so in the video and there's questions at the end, I put a couple of different options. What we find is that for the most part with the reactions we've seen, we only get one product. And the reason for that is that for the most part, in most reactions, whatever is the most stable intermediate will also give you the most stable product. So usually the thermodynamic product and the kinetic product are the same thing, in which case we don't have to really worry about much. That's just your major product. But in here, with this reaction, we have a contrast. Which one is our kinetic product? What does kinetic product mean? Brittany, do you remember what kinetic product is? Right, so it's kind of the fastest and easiest thing to make. So which route would be fastest and easiest to go through? Exactly. So whenever this has a lower activation energy, it's basically easier to climb this hill. So while it's not the best thing at the end of the day, it's definitely the easiest one to get. And so it'd be the fastest one. So this one right here is our kinetic product. Perfect. So your kinetic product is not really based on the product. It's completely based on either the intermediate or the activation energy. Right? Okay. I'm hoping that you did watch that second video, even though you didn't need it. If you didn't, this is probably gobbledygook. You might want to go back to it, but that's the idea. All right, so Angel, what about thermodynamic products? Right. So in terms of thermodynamic product, we're just ignoring everything in the middle. We're just looking at what's best at the end of the day. So which is the thermodynamic product? The blue one. So we have a contrast here. Okay. We can modify the conditions of this reaction to push it one way or the other. So it's not that just one is better and one is faster. We actually can use that information to decide which product we want to get. And it's not about the things that you add, because the molecules we add are the same thing. It's about the heat that we add to the reaction or how hot or cold it is. So let's back out of this for a second. All right. So Chase, do you eat pizza? Okay, so you want pizza for lunch today, let's say. You get out of this class at 11:30. What is going to be the easiest way for you to get some pizza? Okay, yeah, you can order it on the phone. In normal days, you might go to the cafe, I don't know, but there's pretty easy ways to get pizza. All right, what do you think is the best pizza in the world? Okay, Domino's. Let's aim high. Have you ever had like Chicago deep dish pizza? If you love cheese, you might like New York style pizza.
Okay, so we're just.
Yeah, pie in the sky.
I've ever had, not the best pizza available.
Just in the whole world.
Okay.
Where do you want pizza if it's the best one in the world?
New York pizza.
Okay, so you want to go to New York. And this is just an opinion, of course. You might want to go to Rome because you want Italian. I don't know, whatever, right? I think I'm a little lactose intolerant. I'm a lot lactose intolerant. So Chicago, like just a pie full of cheese, not my favorite, but it might be yours and that's okay. So why don't you go ahead and go to New York for lunch? You don't have your own private jet, exactly. So what we have here is a contrast between basically what is easiest, and then at the end of the day, what we would consider to be best. So the easiest is this idea of kinetic product, just what's the easiest thing to get. And then the thermodynamic product is what's best at the end of the day. And the difference between which of those is really, it's about that private jet. It's about resources. So if you had unlimited resources, what are you gonna get? What are you gonna go for? Not the easiest thing. You're probably gonna go for the best thing, right? But with finite resources, you just work within the basically all you can do. And that's where most of us are when it comes to lunch, right? But that's what's happening here. But the resource that we use for reactions is heat. And so with small amounts of heat, which is basically their limited resource to actually make a product, which one do you think you'll get? Again, limited resource, so very cold reaction. The kinetic product, because without a lot of heat, it's really hard to climb these big hills. So you're not jet setting up here. You're walking across campus or picking up the phone and asking Papa John's for you a pizza or Domino's or whatever. Does that make sense? So with the kinetic product, the way that we can gear this and we can choose this is that this will be what you get largely if you do it really cold. So like -70 degrees, 70 degrees. -70 degrees is a thing that comes up in a lot of organic, because that's basically what happens if you take a vat of isopropanol or ethanol and you add dry ice to it. So it's really cold. It's usually around like -70 degrees. So that's practically our very cold reaction. And what we're doing at that point is we're basically taking away all of the heat, making it nearly impossible to climb this hill, and you end up with almost 100% this. Now, on the flip side, if you wanted to get the thermodynamic product, you want to add abundant resources. So what would that be? Yes, so practically, how much heat can you add to a reaction? So think about it in lab. If we were using water as our solvent, how hot could our reaction get? How hot can water get? Right, 100 Celsius, yeah. So, but depending on, it's different depending on your solvent, but what is the same is you just heat it up to reflux. So no matter what your solvent is, this is what we would get. Let's say that it's hot or at reflux. Depending on your solvent, the temperature would be maybe 100 or 97 or whatever, not 68, depends on what your solvent is. But if we heat this reaction up, we'll get mostly this. And if we cool the reaction down, we'll get mostly that. And so it's a really cool thing where this thing plus HCl will give you both of these around room temperature. But if you heat it up really hot, you'll get the thermodynamic product because it has abundant resources to basically clear whatever hill, in which case the only thing that it really cares about is what's best at the end of the day. But if you restrict how much heat it has at like -70, then it's going to be really hard for it to fly to New York. So it's going to basically just take the easiest route and give you the kinetic product, which in this case is a different product. How you feeling? So this is I don't know. I love this reaction because it's the same reagents, but we get to choose just based on how much we heat it up, which is pretty neat. All right, so that's our one reaction for today. That's one of our two reactions for today. How you feeling? So far, so good? Okay, so on a quiz, I will give you an alkene or a conjugated diene and ask you to add HBr or HCl or HI and say either it's really cold or really hot. And if it's really cold, what product should you get? The kinetic product. And if it's really hot, the thermodynamic product. But you need to know which one is which. So you're going to need to go through this. But again, here's my strong warning. You don't get two products because you put that initial H on two different spots. Always put the H on the one spot that gives you the most stable intermediate, and then do the resonance of that. That will give you both products. All right. So if you're not doing a resonance structure over your intermediate, you're doing it incorrect. So work through that. Please practice that. But this is very repetitive. It's the same thing every time. You do the Markov-Makov addition, draw your resonance structure, and give a product from both. Sound good? Make sense? So correct your bridge if you need to. I put a lot of X's and check marks in them. Some of them were perfect, some of them need to work, but that's okay. If we're all good on this now, that's good. We all work through. Just a quick note on bridges. A lot of these bridges are hard, and a lot of them you might feel lost on, and that's okay. I never penalize anyone for getting anything wrong on a bridge anyway, ever. The idea is try and struggle. When we struggle on things, we learn things. If everything is super easy, and college would be a waste of time and money. So please know that the struggle is absolutely fine. And if you have questions, please just ask. But the point is, we'll go through these bridges together. All right, so we are going to look at not just a conjugated molecule, which would have extra stability, but even more stable than that would be an aromatic ring. All right, so here is benzene. This reaction that we're about to do is we're going to spend basically 2 weeks on this one reaction, and it looks the same every single time. It is called electrophilic aromatic substitution, or EAS. So looking at that right now, Avery, what can you tell me? All right, no, just this term, electrophilic aromatic substitution. What do you think we're going to use in our reaction? All right, and what kind of thing are we starting with? Right, and what do you think we're going to do to our reaction? Perfect, exactly. So it ends up, it's different from what we just did because it's not going to be an addition reaction. It's going to end up being a substitution reaction, all right? Which is weird, but it always requires an electrophile and it always requires an aromatic ring. So that's where electrophilic aromatic substitution comes from. All right, here's what won't work. This is what we've just been doing. Nothing will happen to benzene if you add an acid, because while this is an electrophile, it's not a strong enough electrophile. Don't write these things out. If you add Br2, remember that one reacting with an alkene, nothing's gonna happen. If you add MCPBA, again, all that stuff that worked on benzene, or that worked on alkenes last semester, we did a lot of reactions of alkenes. I don't know, cold KMNO4, hot KMNO4, OSO4, none of it works with benzene. Why not? It's really stable. In order for any one of those alkenes to react, you would lose your aromaticity. So your run-of-the-mill electrophiles will not ever react with benzene. So what kind of electrophile will we need?
Fiercely strong.
A fiercely strong electrophile. You need a ridiculously strong electrophile to react with a benzene. And we don't have very many. So we will go through the list of them in a little bit, but for right now, I'm just going to give you one of them. If you take Cl2 and you add aluminum chloride, so this is Cl2 and AlCl3. Aluminum does not have enough bonds. It only has 4 bonds. So it is in and of itself an electrophile. And what we will see is that one of those chlorines from your Cl2 will actually make a bond to it. And you will end up with something that looks like looks like this. All right, but it's going to have charges. So who has charges in here? Let's start with our chlorine. Yeah, go ahead. Yeah, so this coin has 2 bonds, which is unhappy for a chlorine. What charge would it have? Positive, right? And aluminum, neutral aluminum, only has 3 bonds, only has 3 electrons. It's in column 3. So aluminum with 4 bonds would have a negative charge. All right. We have not seen Cl+. We've seen Cl+ one time in this semester, and I don't expect, it was when we made a little triangle with it. That's okay. What do you think the reactivity of Cl+ would be? It's very reactive, but it's a nucleophile, electrophile, leaving group, acid or base. how can it become neutral? Yeah, so your first thought might be it's plus charge, it's an electrophile. But you making another bond to the chlorine would not make it better. A neutral chlorine should only have one bond. So in order for that chlorine to become neutral, what it needs to do is take a bond back to itself, which is a leaving group. So this thing is a ridiculously strong leaving group. We talked about O plus as a good leaving group. CO plus is less stable, so it's an even stronger leaving group. This is a fiercely strong leaving group. And what it's trying to do, because chlorine can pull electron density away from aluminum pretty easily. Aluminum's a metal and not very electronegative. It can't pull electron density away from that chlorine right there. So what it does is it tries to, which makes this chlorine, if this is a ridiculously fiercely strong leaving group, this chlorine right here is basically losing all of its electrons, which chlorine hates. It's a halogen. So this thing right here is being left, it's effectively just a Cl plus all by itself without a full octet, which is a fiercely strong electrophile. So what you're making when you combine AlCl3 and Cl2 is you're basically making a Cl plus, which is horrendously unstable and terribly deprived of electrons and fervently looking for more. And that's the kind of thing that's strong enough to react with a benzene ring. So this is ridiculous. It's ridiculously strong, and that will react with a benzene ring. So while we won't actually just have a Cl plus, this combination of reagents, which is just Cl2 and AlCl3, you don't have to write this out every time. Basically what that gives you is something that's akin to a Cl plus, which would be a, I like it, fiercely strong electrophile. That's going to be one of our list. We'll have 5 of these today, but they all react in the same way. So we're going to use Cl plus, but just know that any fiercely strong electrophile is going to do this. So would you prefer if we use Cl plus or we just write E plus to do generic electrophile for this reaction? Doesn't matter to me. Do Cl plus. Or we're going to do Cl plus, but know that it's exchangeable with any strong electrophile. All right, so we're going to do this with the combination of reagents we would add would be chlorine and aluminum chloride, but we just know that those things together give us something that is akin to a Cl plus, which is a super strong electrophile. All right, so when we have a super strong electrophile, what does it react with? What do electrophiles react with? Same thing we did first out of class. Yep, nucleophiles, or what kind of functional group here? Loosely held electrons in a pi bond. Alkenes, yeah. So it reacts with an alkene. So what we would see here is that this, one of your alkenes, and it doesn't matter which one, because at this point, benzene is perfectly symmetrical, is going to share its electrons with that Cl plus. And so where would that Cl plus go? You've got 2 options. You can go at the top or the top right. Does it matter? No, because both sides are secondary. So if you start with benzene, it wouldn't matter. So we can put it anywhere we want. I'm going to put it on the top right because I have the Apple pencil. All right, and then I'm going to draw out all of my hydrogens because that's a good idea. And so I put my Cl on my top right carbon. What do I have up here? A positive charge. Everybody got good with that? All right, tell me what we have done in terms of our aromaticity. This is an aromatic ring. What about this one? It's non-aromatic because we've got a carbon that has 4 single bonds. Everybody see that? All right, what we do have though, and the only thing that makes this reaction even possible, is that that reaction intermediate is stabilized through the power of resonance. So you end up with multiple resonance structures of this. You can hop this double bond over. This should look very similar to what we did earlier today, which would give us this structure right here. I'm not going to draw all of my hydrogens. because I'm being lazy. Do you think I should draw all my hydrogens? I think probably. So you might want to draw all of your hydrogens. I'm going to ask you a question. Do I have a plus charge in this molecule? Okay, so as I look at this, this is actually a molecule that I could draw that would be neutral. But if it was neutral, that would mean there's 2 hydrogens here. So if you do draw your hydrogens, which look, it doesn't take very long, you can easily and absolutely figure out what the plus charge is. So you can skip drawing your hydrogens, but you need to have the plus in the right place. And if you find that you are consistently doing that wrong, just draw your hydrogens. There's no shame in that. All right, and then I can draw another resonance structure where I move that pi bond over. I'm running out of room a little bit here. I'm going to keep being good though and following my own advice. I'm going to keep drawing my hydrogens. All right, so plus. So what we see is we have 3 resonance structures of our intermediate. So bad news, we lost aromaticity. Good news, we have a lot of resonance. A lot of resonance does not make up for aromaticity. So this reaction, plus we have a plus charge, has absolutely gone up in energy. So we want to get to product, right? And in order to get to product, a benzene ring is aromatic. It absolutely wants to go back to being aromatic. What is the problem with this thing right here that's stopping it from being aromatic? Yeah, this sp3 carbon right here. So what do I need to do in order to have an aromatic ring again? Because you can't have 4 bonds on a carbon and have an aromatic ring. You gotta take a bond off, right? All right. And we already have a plus charge there. So thinking through this, if I wanted to bring a bond over here and restore my aromaticity, do I need to have something leave and take electrons away, or take something off and leave electrons behind? Yeah, do you guys see that? I need to take something off and leave electrons behind. If this chlorine were to take electrons and leave, which is something that we know chlorines can do, then I would end up with 2 plus charges right next to each other. And that doesn't fix my issue. What I want to do is take something off that would leave its electrons behind. So what's easier to take off as a plus charge? Cl plus or H plus? H plus, absolutely. Losing an H plus is just acid base. This is something we have done many, many, many times before. So if you take this hydrogen off as a plus charge, I'm going to write base, but we're going to get to that in a second. Oops, I'll do this in my green here. If I remove that hydrogen, this is the second half of elimination for E1, by the way, but don't worry too much about that. That will let this bond go back and make a double bond. And now I will have restored my aromaticity because, once again, as Chase pointed out, this is my interruption spot right here. It's this sp3 carbon. So what I would get at that point is my product, which is going to still have a chlorine at that spot, but now I've gone back to having double bonds everywhere, and I have gone back to an aromatic ring, and life is good. From a reaction energy diagram point of view, this reaction goes like this, way up and then way down. Because not only did you start with benzene, you started with benzene and Cl+, and Cl+ is tremendously unstable. But what you ended up at the end of the day is a benzene ring and an H+. And an H+ is way more stable. So it turns out you don't need to add another base in this case, because that Cl- that you had left over, Cl- is an atrociously terrible base. But this thing is ridiculously unstable. And by losing that hydrogen there, it can become an aromatic ring. So this hydrogen here is fiercely acidic, because if we lose it, then what we get afterwards is really, really stable. So you don't need to add another base. All you need to add is this. Anything in the atmosphere, anything in your pot will be able to pull that hydrogen off. It doesn't take very much. But what that does is it ends up with, this is a big picture of a reaction. All we've done is we changed out a hydrogen for a chlorine. So it's a substitution, but it's a way different substitution than SN2 because there's not a nucleophile that comes in and kicks off a leaving group. It's actually that you add an electrophile and then you remove an H plus. And so big picture, it's not that big of a deal. You just take off an H and replace it with chlorine. And where it happens, if you start off with benzene, doesn't matter because it can happen anywhere. And it turns out that while drawing these resonance structures can be informative to us, you don't actually need to draw the resonance structure to get to your product. You see, we just went through the first one to get to our product. So at the end of the day, this reaction is benzene with an H somewhere. I'll just put one right here. And Cl2 with AlCl3 gives us so it's electrophilic because you need to have a really strong electrophile, aromatic because it's all on an aromatic ring, and substitution because you take something off and replace it with something. Any questions? All right. I am going to tell you about the other 5 electrophiles that we have, or the other 4. So these are, we're going to go through 2 more of them next week. So we're going to have 7 different strong enough electrophiles to make electrophilic aromatic substitution work. For this outcome in this week, we're only going to go through 5 of them. The other 2 are more complicated, so we're going to kick those until next Friday. But here's the 5 to worry about. So here are our 5 fierce electrophiles. And these are all for electrophilic aromatic substitution. Right. Number 1 we did already. It is Cl2, excuse me, and AlCl3. And that is going to give me something that's approximately a Cl plus. And that will be what is functionally going to be the electrophile that goes onto your benzene. So we would turn a benzene ring into a chlorobenzene. All right, the second pair of reagents, oh dear, not want to draw in yellow, is Br2 and iron bromide. You might notice that aluminum is in row 3 of the periodic table, and it makes pretty reasonable bonds with chlorine because they're both in the same row together. They're both about the same size. They use the same orbitals. Bromine is 1 row down, and so bromine makes stronger bonds and stronger molecules with things about the same size. So we tend to use iron bromide instead. So aluminum bromide exists, iron chloride exists, but just in terms of these reactions, the aluminum doesn't really do anything. The iron doesn't really do anything, but the reason that we use iron with bromine and aluminum with chlorine is because they make more stable molecules that make more reasonable bonds. All right, so we could draw out the mechanism of this one. It's going to look exactly the same as that one. What do you think this is going to give us as an electrophile? Take a wild guess. Yeah, it basically just gives us something that is structurally similar to Br plus. So those go pretty well hand in hand. All right, following the trend, that's chlorine and bromine. We can also do this with iodine. With iodine, we don't usually use a metal reagent because, as you might remember from mass spec, if there's iodine in there, we would see an I plus, and it would have a peak at 127. I know it's been a while, but the farther down you get in the periodic table, the more stable they are with a plus charge or a minus charge. So it's actually a lot easier to get an I plus than it is a Cl plus or a Br plus. So all we really need to do is add an oxidizing reagent. And what we usually add for this is nitric acid. So iodine and nitric acid are going to give you I plus. And it's not something that's kind of like I plus, it's just literally you get I plus. And that's going to be a fiercely strong electrophile, and that will react with the benzene. So in the case of this first one, it would turn benzene into benzene with chlorine. The second one would turn benzene into benzene with a bromine. And this one would turn benzene into benzene with an iodine. And all of them remove a hydrogen. That's your substitution. They all go through the exact same mechanism. The only difference is instead of sticking on a Cl plus, you put on a Br plus. Have you guys seen benzene drawn this way? Okay. There's another way of drawing benzene that's even just faster, which is a 6-membered ring with a circle in the middle instead of the double bonds. It means the exact same way, same thing. You'll see sometimes I don't tend to draw it that way. My preference is to do it with double bonds, but some people draw it this way. They prefer it because it's faster, I guess. Also, you know that the double bonds are like always moving in a circle. There's resonance for benzene. So it's really hard to say exactly where they are. So this is kind of the idea here, is that through resonance, they're moving through it over and over again. So sometimes you'll see benzene drawn that way. Just, that's a public service announcement. I'll never draw it that way. You can draw it that way if you want to, but that's what benzene is. All right, number 4. All right, this is a pretty weird one, but if you combine nitric acid and sulfuric acid, both of those are really strong acids. And strong acids like to protonate other molecules. But in the case of 2 acids put together, I mean, this is kind of like you're putting 2 predators together and one of them is going to eat the other one. It turns out that sulfuric acid is stronger than nitric acid, and sulfuric acid will actually protonate nitric acid and make nitric acid fall apart. I can show you the mechanism if we have time, if you want to, but what happens here is that sulfuric acid puts a hydrogen on nitric acid, which gives it 2 hydrogens, and those 2 hydrogens leave with an oxygen. So basically ends up removing water from nitric acid, and you end up with NO2, which looks like this. So NO2 with a plus charge, think of it from this nitrogen's point of view. That nitrogen has basically, it's kind of like 2 carbonyls. It's got those double bond O's. So remember, carbon in a carbonyl is an electrophile because oxygen's pulling its electrons away. So nitrogen in a double bond O would have the same situation. Oxygen's more electronegative, but it's got 2 of those and it has a plus charge. So that nitrogen is super deprived of electrons. And so that nitrogen right there is one of your fiercely strong electrons. And so the result of that is that you can put an NO2 onto a benzene ring in exactly the same reaction. You'll lose a hydrogen and replace it with NO2. And that is a nitro group. So a nitro group, a couple of weeks ago when we were talking about how you could oxidize and reduce different molecules, I think that was outcome 8, maybe 9, I don't remember. But I mentioned that nitros are something you could reduce down to an amine, but that we hadn't really seen nitros before. Nitros don't often go onto alkanes, but it's really easy to put them onto aromatic rings through electrophilic aromatic substitution. So this is where we mostly see nitro groups, is directly attached to benzene. So that's why we haven't seen them until now, because we haven't talked about benzene until now. But you can, this is called nitration, but you put an NO2 onto a benzene ring. All right, number 5, our very last one, is fuming sulfuric acid, which is SO3 and H2SO4. In this one, it doesn't make an electrophile. It's just that this guy already is a very strong electrophile, that's sulfur. It would look like this. No, this is going to look weird. But as you can imagine with that nitro group, the sulfur is having its electrons pulled away by oxygen, which is more electronegative. So that sulfur right there is your electrophile. And then it would go onto the benzene ring exactly how it is, which would make an SO3, but it would actually make an SO3 minus, and because you have it in acid already, it makes an SO3H, which is a sulfonyl group. So sulfonyl groups are not a thing that we've talked about. Sulfonyl groups are really, really present all over the place in biology. And so sulfonyls are things kind of like nitros. Sulfonyl is kind of new. It's not a functional group I'll ask you to name, but these are our 5 fierce electrophiles, all of which can get stuck onto a benzene. And the mechanism for all of these is the one that we just did already. So it's exactly the same one that we just saw. Any questions on this? Yes, sir.
Why don't you do anything with the other resonance?
It's a good question. All right, so let's look at these other resonance structures right here. So the idea is we want to restore aromaticity. And looking at all of these, what's the same spot that's blocking our ability to be aromatic? Still,
Or the CO.
yeah, so it actually has nothing to do with where the plus charge is. It's all about, it's this carbon right here is blocking up our aromaticity. It's the same carbon in all cases that blocks your aromaticity. And so in order to have that carbon lose its hydrogen, no matter which one you were looking at, you would have to remove that same hydrogen. And so you could do it in all of these cases. You don't have to. But in all of these, it's not like you do a reaction at a different spot like we did in that first reaction for that first half an hour. Because it's elimination and the same hydrogen is gumming you up, what you'd have to do here is take that hydrogen off, and these electrons would then maybe go like left, and then that would hop over, and it go the exact same product. And then for this one, what we would do is, because we kind of switched where our positive charge is, take that hydrogen off, these electrons could go clockwise, give you the exact same product. So they all give you the exact same product, so that's why we don't really need to draw them up. For Monday, we're going to look at what happens when you don't just start with benzene, you start with like toluene or phenol or something, in which case the resonance structures tell you everything about where your second thing will go on. But if you just start with benzene, it doesn't matter where you do it. The resonance structures, while they're there, don't really impact. All right, questions on any of this? I'm going to give you an example reaction. Here we go. Do. All right, I'm gonna start with benzene. I'm gonna add Br2 and FeBr3. Draw that out, if you will, and draw me the product that you're gonna get. In fact, I'm gonna ask you to draw the mechanism. What? So I tell you what, so that we're all on the same page, react to this pi bond right here, top right. Don't look back. I know you could find it. Dang it. It is absolutely okay to do it wrong. Just give it a try. I am here. I will walk around. No. There's no better feeling than not being able to do something one day and being able to do it the next. That means you're learning things. I prefer failing the first time. That's how I learned all my lessons. Start with the icon, here. So that your bromine will go with, right, and what would you see here? Perfect, exactly. Great. If you want to, you could draw the resonance structure as you go. So after that, it doesn't do it. The pylon is actually gone. So you get a PR on one side, something else. All right, good. So it's okay. So why is this non-aromatic? Well, it's not because the bell bond's gone. It's because that carbon has 4 single bonds. So what we need to do in this step is get rid of one of those. So just write base and take off what you need. Lovely, that's perfect. You're getting there, yeah, this is just right. So you're taking off that ion, perfect. So we're missing something. What else should we start with? What makes sense? And tell me what's going on with this part. There you go, perfect. Good. No, don't understand, it's good. Yes, because this is not a Br minus, it's adding electrons in. It's a Br plus, it's pulling electrons away. So the arrow should go from that pi bond to the bromine, but then this is correct. because the pi bond will make a new bond to your bromine and you have a plus charge. Right? So the base needs to pull that hydrogen off, and where would these electrons go?
Go back.
Yes. Exactly. Exactly. Okay. So that makes Br plus, the arrow goes from back to Br plus the third system. So this, you can kind of just do it all at once. So if base grabs that hydrogen and leaves electrons, they don't kind of have to turn into a lone pair and then become a double bond, you just move it straight line. So that's perfect. Okay. Got it? You got the hydrogen off? All right, so base has the electrons, so this arrow should go the other way. Right, it shares electrons, it makes a new bond with that hydrogen. And then the electrons, they were holding the hydrogen. So they should just arrow this with line. It looks perfect to me. Except for this would be, so this isn't a Br minus sharing electrons in, it's a Br plus that pulls electrons in.
Okay.
So this is great. The arrow here will go the other way because the base has electrons that share with the hydrogen.
Yeah, so
And
then.
then the electrons for the pi bond. So that CH bond. So in most acid reactions, base shares electrons with the hydrogen, and then whatever was attached to the hydrogen, basically. Is that all perfect? Yes, it's perfect. Yes, yes, great. That's going down to the, yep. Yep, great, wonderful. Good job, everybody. So remember, pi bonds. You're good. Pi bonds always go to the electrophile. We're not adding a nucleophile into the benzene ring. We're pushing electrons out to the electrophile. So all of you guys did this correctly, but for those of you in Zoom, this is how this would work. The pi bond goes out and makes a new bond to bromine. You could put it in either the top or the top right. I'm going to put it in the top right because that's what everybody in the class did. Then you get a plus charge right here. And then the second step, you would have a base, which it wouldn't matter. In this case, it's actually going to be the Br minus. In a lot of those, it's just water. But what that's going to do is take this hydrogen off, because this carbon right here is what's stopping your aromaticity. So that's the one you need to focus on fixing. So we take a hydrogen off. Now that carbon only has 3 bonds. The electrons from the hydrogen move over. So this is acid base. Remember with acid base, base shares electrons with the hydrogen, making a new bond to a hydrogen. The acid takes electrons back from the hydrogen. Usually it becomes a negative charge, but in this case, it doesn't. The electrons just hop on over to make a new double bond, but basically putting electrons back in. And that would give us And what have we changed overall? Big picture from starting material to product. Exactly. It's the only thing that changed. So if we started with a benzene and we added iodine and nitric acid, we would take off an H and put on an I. If we started with nitric acid and sulfuric acid, I know, I told you this once 5 minutes ago. I don't expect you to remember it. What we would do is, I'll just go back and show you. If we added this nitric acid and sulfuric acid, you take off an H and replace it with a nitric. If you add SO3 and H2SO4, which is fuming sulfuric acid, you take off an H and replace it with an SO3. So those are just 5 things we can put on a benzene ring. It's a substitution where you just remove a hydrogen. All right, any questions? You guys should practice this, but that's it. We feel good right now? Feel like we can do this? Good, good, good. So on Monday, we're going to add more rules to this, but not any more reagents. So you need to know how to do this reaction because we're just changing the parameters, but it's the same reagents, the same reaction. Thanks. I hope you all have a lovely weekend. It's a beautiful day. Go Bears. We're all getting vaccines. Guys, there's hope in the future. It's out there waiting for us. Thanks, everyone.